Sorry about that. Okay. All you need to do is split it. If it's adding to the reactants, then it's going to be endothermic because you're gaining heat. Now, you may say something like this, right? Where it's on the right side, where it says plus. Now, that doesn't mean that it's gaining heat. We're actually losing heat. So it's exothermic. Now, how does that make sense? Well, these are the two reactants, obviously. However, this, don't even worry about that plus sign. This is the products. It may be a little bit harder to decipher, but just think about it. It's on the right side, so we're exothermic. Can never have minus heat in these types of equations. Now, this one, it's saying this plus this equals H2O plus this amount of energy. This is exothermic. It's exothermic. Now, you would actually write it as, don't worry about that. So, yeah, it's exothermic, endothermic. Cool? Jeez, I'm probably going to lose my voice. All right. I can use thermochemical data to create an energy profile graph. Oh, yeah, we can. Right. Easy enough. All right, here's what we're going to do. So, let's say we have in our whateverness, let's say we have 2 H's, or 2 hydrogen, 1 oxygen. Now, we have to add those together. However, to do so, we need to put in 100 kilojoules of energy. 100 kilojoules. Now, just looking at this equation, and I'm going to set it over here as the actual equation, H2O. What do you think its type is? It's endothermic. No. Yeah, it's endothermic because it took in this energy to get this. How would you graph this? Well, we need a starting amount of energy, or a starting amount of whateverness. So, generally, you're going to have something like this. Again, we're coming back to here. Kilojoules per mole. 250, 350. All right, so let's go ahead and model that. So, what this is going to look like is on a graph, right? We're going to have like this. Let's say, just as an example, we're starting at 1,000 kilojoules per mole. Kilojoules per mole. Now, a mole, that's a bit harder to explain because it's like another type of, like, remember the joules per whatever? That's, like, what that is. That's how you measure, kind of how you measure enthalpy, I guess. But a kilojoule per mole, if I can find it in these papers that are so necessary. Thank you. Yep. A single mole is 177.8 kilojoules. Now, don't memorize that. I wouldn't expect them to have that on the test, right? But I just wanted to show you that to you. Now, 1,000 kilojoules per mole, let's say the final reaction is 0. Now, what we're doing here is this equation. Let's just say this, because this starts at 900 kilojoules. Right around here. We'll actually label it as well, just for you. 900 kilojoules. Reactants. Oh my gosh. Reactants. H2 plus O. Yep. Now, we're adding 100 kilojoules, but we're lowering. So that's an exothermic process. All right, I think I figured that out. So the initial reaction is endothermic because it takes in heat. However, in general, it's going to be exothermic. I'm sorry, you can look that up. I can't explain that to you. I don't know how this makes sense, but I guess it does. So that's how we would graph this. H2O, and don't forget to put 100 kilojoules up here. And that's basically how you do it. Now, this is specific name, so if it pops up in the test, just remember that area has a specific name. We're going to go on to the next thing. Actually, honestly, guys, I think the better explanation to this is not like that, but it would be more looking like that. Sorry, not like that. It would more look like that, okay? So just imagine it look like that. Now, our next learning target is we've already done. I can use thermocoequation. Sorry, okay, hold on. I can analyze an energy thermal profile. We already did that. This is exothermic. That's exothermic. That's endothermic. Boom. So that's one of the learning targets already done. I can write a thermoelectrical equation from data or an energy profile. Well, obviously this is simple, so you just go, oh, the reactants, H2O. We added 100 kilojoules to it. Yeah, we added 100 kilojoules, however, we ended up losing, like, what is that? Like a 999 or 990, sorry, kilojoules. So in total, the process is going to be endothermic, however, it's like that. So honestly, you can write that. It's really simple. And then I can use a thermoelectrical equation to draw a profile, and we just explained that. So I can predict reasons why an energy profile might deviate from the expected results. Easy. Why it might deviate is, not everything's perfect. You're not going to have the perfect amount of everything, so something might change, right? Done. Learning target 4. We're finally onto that after, 2 billion parts. I can explain the difference between temperature and heat. We've done that 10 times. I can explain the concept of specific heat. I actually did that for you already. The concept of specific heat. Water. Water specific heat is 4.14 joules per kilogram C. What this means is that per 1 gram, sorry, that's a gram, per 1 gram, it takes 4.14 joules to heat it up by 1 degree Celsius. That's super simple, right? I can identify mass, specific heat, initial temperature, and final temperature in a given scenario. You should be able to do that on your test. It wouldn't be too hard, all right? I can identify mass, specific heat, initial temperature from data. From data, that's just like a word problem. You should honestly be able to get that. I can't exactly go over that, but that's not that hard to go over. Just look for these specific symbols, or if it says specific heat, mass, final temperature, initial temperature, you should be able to find that. If it asks you to find it, oh, one very important thing. There are different equations for this guy, right? Obviously, the original one is like that. If you want to find mass, this is the equation for mass. That's the equation. If you want to find specific heat, this is the equation for specific heat. Remember, if you're not finding, if you're not going to find the gained heat or loss, then you're most likely going to be putting Q on top of the rest of the equation. Simple, right? All right, I can calculate heat absorbed or released by using mass, specific heat, and temperature change. Heat absorbed or released by process. Okay, that's super simple, right? Easiest way I can explain it to you is through an example. Let's say we had a pot of 100 grams. We're measuring grams. Liters, I think, is what they would usually measure in, of water. Now, usually on the test, they're going to ask you to do it 4.14. They're going to ask you to do it 4.14 for the specific heat of water. That is the specific heat of water. You don't need to memorize that. Now, 100 grams. It's heated from 0 degrees Celsius to 200 degrees Celsius. Now, what is the heat that was gained by it? Easy. You remember our thing. Also, make sure whenever you do the equations, make sure you put the units, because she will take off points like it is crazy town doing that. She will take off points every time. She will take off your points if you don't put your units. I sure hope this isn't moving. I sure hope my thing's not moving. Here. Whatever. So, this equation, Q, is I'm not going to solve it for y'all. Y'all can do it with the calculator. That's easy. 100 grams times 4.14. This is going to be joules per gram of C. Now, our heat change is going to be 200 minus 0. It's always going to be the final minus the initial. That is your equation. All right? So, and let's just say we calculated it. I can use energy absorbed or released to calculate mass. So we've already done that for you. Remember, it's these other equations.